So, as I mentioned last week or this week, so earlier in the week, we are really mainly going to just cover IR, spectroscopy, and mass spectrometry, because those are kind of important chapters, generally in chemistry and in biology as well. And so I think it's useful for you to know something about this. I will also use this session just a little bit for a review. So we can cover some parts of particularly chapter 11 as well as chapter 12 that you'd like to give a little bit more information. So we will start out with me just going over the slides that I have on chapter 11, and particularly then tell you more about IR spectroscopy and mass spectrometry. And then whatever time we have left, which will be possibly quite substantial, maybe half an hour, will be open for any kind of questions that you have, just as a review or recitation type of session. I'll be happy to go into any of the topics that we cover, including those of earlier chapters as well, if there's any interest. Up front, do you guys have any questions? Anything you'd like to ask about any material we've covered so far, or logistics? So unfortunately, I can't tell you much about the final. That's still in development. I'm getting emails every day about some fine-tuning of the plans that it has. All I can tell you is personally, as long as things are continuing the way they are, I would still strongly recommend you to take the final. Just prepare regularly and take the final. Now, if there's anything unusual happening, obviously we have backup plans. And for whatever reason you choose not to take the final, I'm sure that I can find an accommodation. In my experience, you can trust me that, again, you're best off if you do take the final, because then you're done with the course and you can move on and do other things after that, rather than something where you have to come back and do some other exam at some other time. It won't be immediately, right? We have a backup plan for the final in terms of the room, the location, which I will be able to tell you about shortly before the final. These things are still being formulated and hashed out, but I've been told that there is a backup room, and that I will only know about this backup room location like a day or two before the final, actually, and that will let you know through courseware. So you'll get more information in the final week through courseware. So there's a location backup, so you can be sure that there will be a physical final presented here on campus, and I will be there and we'll hand it out, and whatever happens, we'll definitely sort through that. It's no problem. You can also be sure that if for whatever good reason, if you have a good reason not to take that final, then there will be some option that you'll have. But again, in my experience, it might look attractive to do that, but you're still better off taking the regular final, because you'll have to learn the material later, and there are other things that you might have to do. So my personal recommendation clearly is that you just take the final, you plan for it as best as you can, and then you're done with the course. Also keep in mind there's a second session to this class, and that's Chem 32. So it really will depend a lot on how well you've done in Chem 31, how well you know the material. You'll do a lot better if you actually study all these chapters, particularly the last 6 chapters, 7 through or 6 through 13. Those are important chapters, and you'll see many modifications of the things we're learning right now in Chem 32. So people that have done well in Chem 31 usually have a very good chance to do pretty well in Chem 32, particularly if they've done well in the second part of Chem 31. So again, it's in your interest to kind of really try to do as well as you can, learn the material. It's a good investment. And finally, there is the way these courses are being taught, certainly the way I teach it, the whole course kind of forms a unit, and so it makes sense to kind of just go through the end and do all the work that's necessary for the different exams, because they do give you the best chance of getting a good grade down the line. So I wouldn't, if I were you, I wouldn't really, certainly wouldn't worry about the exam being held. It will absolutely be held. There's no doubt in my mind that there will be an exam on Wednesday in 10 days. Location, probably here. There's a backup. We'll be able to do it. So you will not study in vain. Okay? There's no question that we will not just postpone the exam in any way, and you'll have it a month later or a week later or something like that. But when you study I will make sure that you have a chance then to come to the conclusion as the course, and get a decent shot at being able to do well in the final exam. Okay, any questions for that? Again, I know very little, and things are still developing, so I don't want to spread too much information that then we have to change. That's very confusing. But I can guarantee that, to the best of my knowledge, there is a 100% chance that there will be an exam as scheduled, and it will probably be in this room or in a makeup room somewhere. And so there are plans that will prevent us from having to collect all the exams, and then we'll have to figure out what to do next. So we will certainly work. I even have an option in mind that we can even interrupt the exam and go somewhere else if necessary. I hope that won't be necessary, though. And right now I'm pretty confident that we'll have a regular exam. So just prepare for that as to the best of your abilities, and I think that will work out okay. Okay, so when we look at the material in this chapter of alkenes, and again you've seen already in chapter 12 that we'll pick up a lot of these topics. We essentially went through a lot of the chemistry, regiochemistry and stereoselectivity, stereochemistry rearrangements that are being elaborated more in depth. And in terms of structure elucidation, which was one additional component here, we've already covered NMR in the previous chapter, and we also encountered the index of hydrogen deficiency. Again, this is just table 11.6. I want to highlight that to remind you that these degrees of unsaturation or the index of hydrogen deficiency are very important, giving you an idea about some of the basic structural features. The numbers of rings, numbers of unsaturation, double bond counts as 1, ring counts as 1, triple bond counts as 2, and then you have these combinations where you have 2 double bonds and 1 ring, which would then add up to a total index of hydrogen deficiency of 3. And you can calculate this by the 2n plus 2 rule. Number of carbons times 2 plus 2 gives you the hydrogen number in a fully saturated system. So then you subtract that number you subtract the hydrogen number in the formula from that number divided by 2. That gives you the index of hydrogen deficiency. So it's very easy to get a good idea up front what are feasible structures. Okay, let's go and look at the IR, straight on in the IR spectroscopy. And I have this slide with 2 of the instruments that we are using. At the bottom right, we have nuclear magnetic resonance. We have a big pot here that is the magnet. The magnet is a shielded magnet. It's superconducting, but it's very cold. You have to have liquid helium inside, followed by a mantle, or surrounded by a mantle of liquid nitrogen. And that, of course, leads to a fluid-like, thermal-like arrangement here. There's also a considerable magnetic field. And so this is actually an old magnet, which is not shielded in particular to contain a magnetic field. So you have to be quite far away if you have any kind of magnetizable items, or if you have a pacemaker or so. That's of course very dangerous. But you shouldn't bring any metals very close to these unshielded magnets. The newer magnets have also shields around them that dampen the magnetic field that comes, which is very strong. And that allows you to stack them a little bit closer together. In an MR room, you can have several magnets lined up much more closely. And also it's not as dangerous in pulling stuff into the magnet. Those are extremely strong magnetic fields. So the actual magnet setup is here. Your sample goes in here, the sample inlet, and is immersed roughly in the middle of this superconducting magnet. And you can actually have a little ladder here that you can use to add the samples and take them back out when they're ejected to sort of compressed air. They're also spinning in order to overcome the inhomogeneous character of the magnetic field, to make them more homogeneously exposed to the magnetic field. And then here you have the console. So overall, this is a pretty significant size. You can see here a trash pocket or so. I mean, it fits well into a room, but it is large. This is an IR instrument from my lab. And it is, compared to this, it's absolutely tiny. You can see, I think this is a mouse or something, glasses or so. But from here to here, this might be, something like 10, 15 inches diameter. You can lift this around, you can walk around, you can take it home, do your IRs at home if you want to do so. It goes with the computer, of course, the portable computer as well. This is all the bench stuff. You can see here in the back, this is the portable computer goes there. So this is roughly the size of a portable computer, a little bit larger on the dimension, the Z direction here, and it's also a little bit heavier. And you actually take your IR right here, you put your sample here, and you can put anything here. It doesn't need to fit into a tube and into a magnet. You can put a big piece of the sample here and analyze it. Okay, you have a sheet of paper. If you want to analyze your finger, a nail, a hair, anything you want, you can put it here and get an IR analysis. So why does size matter? It's because it's a portability and also ultimately the cost, the efficiency of these systems. You can walk around with them. It's hard to walk around with an NMR. So these are being utilized as portable analytical stations. You can even miniaturize them even further. Obviously, this is not the smallest you can go, but this is a handy instrument, and it's very convenient for a quick analysis. You can bring it into any kind of environment very quickly. So IR is still useful, not so much because there's a lot of information you can gain, but because it is a very compact analytical technique, and it gives you, if you have a comparison sample, an almost certain match. So you need a database. You can analyze the structure a little bit based upon the principles that you're going to look at. But the big advantage here is that every compound has its fingerprint, and so if you want to just look for specific compounds, you can very rapidly get an idea if this is the compound that fits the data in your computer, in your database, and then the sample that was measured. And there literally are IR spectra of 2 to 500,000 compounds that you can purchase, that you can, with a software, with an algorithm, you can search for similarities in very large data sets. So it can be very quick, very little material necessary, in all kinds of forms you can get a match with the structure. And so if you go out and you work for a company that does any kind of analytical work, produces anything, or looks at quality control, you will always find IRs just because they're cheap and they're convenient. So chances that you're going to run into IR analysis in the future are actually considerably larger than NMR, with the exception of MRI. Yep?
In regards to more portable ones, does this by chance have pulse oximetry measures oxygen content in the blood?
I'm not sure how the oxygen content, I think that is through UV spectroscopy. So I think it's not IR, if I remember correctly. A lot of the analytical methods in the clinical lab are based upon UV visible spectroscopy. That's partially because of sensitivity. So I think that is not the way it's done, but in fact you can see water and oxygen and CO2 and things like that in the IR, but it's much more commonly used for polymer samples, any kind of materials. I guess in materials research it's much more common than in the clinical lab. Sometimes because of the complexity that you need another tool to kind of, through an antibody reaction or a colorimetric reaction to identify a particular component. So oxygen analysis very often goes indirectly via analysis of hemoglobin, and that's usually a UV technique. Okay, so what do we need to know about for infrared spectroscopy? Well, infrared spectroscopy measures vibrational modes. And so vibration is exactly what the word says. It essentially measures the stretching and bending, compression as well, of chemical bonds. And so the other information that you get through IR spectroscopy, you actually indirectly get the strength of a chemical bond by measuring its ability to extend and also to be compressed. And so we're looking at localized vibration. So an advantage of IR spectroscopy is that essentially the combination, the IR spectrum, is a composite of so-called localized vibrational modes. And we have some very simple vibrational modes. In this case, for this molecule, let's say this is methane or another hydrocarbon, we have a carbon-hydrogen bond, and this single bond can be extended and compressed. And that is the so-called stretching modes. A very obvious, straightforward way to kind of analyze an organic molecule, and the energy that is absorbed in vibrational spectroscopy directly leads to a selective stretching of such a bond, and we'll see what the frequencies are in order to do do that. There also are coupled mode where you essentially do 2 bond modifications simultaneously. And if you look at this molecule, it's 2 CH bonds. You can obviously have a symmetrical mode where you pull on both bonds simultaneously, or an asymmetric mode where you pull on one and decompress the other. Those are 2 different motions. And so those are the very straightforward stretching modes. Again, a simple stretching and the coupled stretching. And the coupled stretching has both a symmetric and an asymmetric component. And then you can have bending mode, and those of course now deal not so much with the distance between 2 atoms in a molecule, but with the angle between different atoms, at least 3 of them, right? That makes a bond angle. So we have bending modes, we have a bunch of those in plane and out of plane deformations. And here we have the sistering mode, where you bend these like a sister. And we have a rocking mode here, where it essentially is an asymmetrical mode. This is a symmetrical bending, this is the asymmetrical bending, cold rocking versus sistering. We can also do the bagging, which is out of plane, and the twisting. Again, this is bagging is symmetrical. We're doing the same thing for both bonds. They remain symmetrical. And in the twisting, we're doing the opposite motion here. And so these are the out of plane deformations. And so I have a very nice program. It's an old program. Doesn't need to be new though. And it is old enough that it doesn't run on my Mac here, which is why I have started up the Windows interface. There we go. It's called IR Tutor. Let's see if I can get my mouse there. Okay. So there's a little bit of theory here, but we're going to go straight to actually looking at spectra. Because we can visualize this very nicely. And so what we're looking at here is just the hexane molecule. And this is the IR spectrum of hexane. And you can see that we have here an axis that's from 0 to 1 that essentially gives us the level of absorption, the amount of transmission or absorption. This is transmission here. So transmission 1 means that all the energy, the vibrational energy, the vibrational pulse that we apply is transparent. It goes through, nothing is absorbed. When we go to 0, essentially everything is absorbed in the system. So we get the peaks here, which means that when we have a peak of this sort, we get essentially resonance. We transfer this energy because there's a resonance equation that's fulfilled, very similar to what we saw in the NMR spectroscopy discussion. And so this is the spectrum, the entire spectrum of hexanes, and we can see there are 3 regions here. There's a region here with very strong absorption, where we have very low transmission, right? And we have a region here where we have kind of an average medium absorption or medium transmission. And then we have a gray area here with a little bit of a peak and some ugly, what looks like a background type collection of bumps here. So some sharp peaks and then a bumpy region here. Okay. And you can see we can expand these regions, but before I do that, let me actually click on one of those. Okay. And so I clicked on the second one here. And so now in the sketch here, you see what this is. Okay, you can see that this is a stretching. So these are the stretching regions here. Okay. Whereas you're going to see we have more of a bending region here. And then these are the kind of combined modes where lots of things in the molecules are going on. So this is the anti-symmetric stretch, okay, that is absorbed here. This part of this big peak at about 29, 26, about 3,000, a little bit below 3,000 so-called wave numbers. And these are inverse centimeters. This is an old CGS system that's used here. So the energy is translated into wavelengths, and this is the inverse wavelengths here. So it's over inverse centimeters. And so this gives us an idea. And in fact, the closer we are to the inverse wave number, the higher energy, the vibrational energy is that we are using here. If we go to lower wave numbers, then at that point we would have lower energy vibrational transmission. So this is the CH2 anti-symmetric because when we elongate this, we push this in. Okay, so it's anti-symmetric. One bond is expanded while the other one is being contracted, and of course vice versa. So this is exactly this mode. So if we irradiate hexanes with vibrational radiation, that has a component at 29, 26, And we're actually starting to access these methylene groups, and they start to move like that. We're pumping energy that populates this particular so-called vibrational mode. That's where it absorbs. And the absorption is shown here. So this particular IR light here, it comes from an IR light source, is being absorbed. So rather than going through the sample, this is actually energy that is being retained in the sample. And when we look at the slightly higher peak, only a few wave numbers higher, then we have an antisymmetric stretch of the CH3 group. And it's always, you can see how narrow this is. It's very predictable. If you see absorption here, we know this molecule has CH2 and CH3 groups. So basically, through the stretching absorption here, again, antisymmetric, you can see that one goes out, the other ones go in here. We can for sure say that there is a methyl group in this system. If there is no methyl group, we wouldn't see this particular peak. Okay. There's another one. Over here, the third one, which is usually distinct. You can see sometimes these are very, very close. This is the distinct one. This is the symmetrical stretch. You have seen the asymmetrical stretches before. In the other two modes here, they're a little bit at higher wave numbers, a little bit at lower wave numbers, usually a distinctive peak. Sometimes, of course, the resolution is not that great, and you have just one combined kind of a band here. But here, it's nicely separated. That's often the case with instruments. You can see the symmetrical stretch, and you can see it's a few wave numbers lower. So between 2800 and 3000, on hexanes we have either 2 or 3 different bands. They are typical for the CH3 and the CH2 groups here. So we can immediately assign those. Okay, so in this range we have stretching. And then what do we have over here? What are these? And so here we can see this is roughly at 1500. See how old this is. But it still works. It's a nice program. Okay, there we go. Okay, so these are now the bending modes. So we're not changing the bond distance anymore, but we're changing the bond angles. And so this is around 1460. It's an antisymmetric bend of the CH3 group. And that's exactly how the motion looks. So physically, that's when we pump in this energy, that's how hexane reacts. We start to populate this particular mode. You can see there's another peak very close to it, and that's the CH2. So very often you have the CH3 and the CH2 very close, and these are both bending modes. You can see this is our scissor bend that we've seen before. So we have the CH3 and the CH2 bending around 1455. That of course confirms that we have indeed in this molecule CH3 and CH2 groups. And here the two are very close. You can really distinguish them. If they weren't color-coded, it would look the same. Okay. And then we have the CH3 symmetrical umbrella. That's a 1375. Okay. And again, that's a very typical, slightly different mode from what we have over here. So this is a symmetrical bend. If I go back and look at this bending over here, okay, you can see this is the asymmetric bend. So this is asymmetric, and this is symmetric. It's like a breathing bubble. Okay. And they're distinct. And again, this is a little bit a smaller peak, but very typical, usually comes together with this peak. And you only see this if you do have the CH3 group. Okay, what about this part of the molecule? This is the fingerprint region. Remember I told you that in addition to having all distinct groups that give distinct peaks, a molecule also has a very undefined but good way to identify a typical absorption, and that's the fingerprint. Now for hexanes, that looks pretty bad because we have just some kind of a noisy background over here. But as you will see, if you have more functional groups, this becomes very distinct, and we can help to identify a particular compound. So with the help of these regions, you can actually differentiate between hexane and decane. Because decane will have a different fingerprint region, but otherwise very similar peaks because it has CH3 and CH2 groups. So the peaks will be similar for decane, but this part will be different. So it is used, as it said here, to positively identify the sample. So that if you have a large database and a fast computer, you can then use this region and figure out, by comparison with many different spectra, that in fact you have a sample of hexanes here. And that can be important. Now, let's say, for example, that it always smells bad in your backyard, and you are suspicious that somebody pumps, a hydrocarbon in there to get some of the gas out, or whatever they want to do, extract something out of it. You can take a sample, you can analyze it, you can look for the gaseous component, and then things like that can be measured and can be used to identify in a very convenient way the contaminant that you might have, in the ground or in the air around your house or in your basement or wherever you are. And again, the advantage of the instrument you've seen, you can immediately take that and put it to side wherever it is, in the forest or anywhere else. Very portable. Finally, last peak here. So this is some kind of this is now would be the group exercise. This is the equivalent of having a party. There are a bunch of people here together, a bunch of CH2 groups, and they all rock at the same time. This is in fact referred to as the rocking mode. And it is at 720 wave numbers. Okay, so stretching, bending, fingerprint, and then we have some kind of group modes. Group stretching and bending mode, mainly bending modes of the entire functions or chains that do things in concert. Okay, so that is hexane, relatively straightforward. Let's look at the whole thing together. These are the different CH3 typical subparts of the spectrum. This is all indicative of a CH3 group, and this is all indicative of a CH2 group. And of course, that covers hexane pretty much, right? Okay, now let's look at the branched hydrocarbon, and you can immediately see how much different that looks. Okay. If I would give you the proton NMR, I can tell you the difference between the two compounds would be, it would be there, but it would be, a lot of it would be difficult to figure out. It wouldn't be as different as this spectrum is, IR spectrum, and the dimethylbutane spectrum and the hexane spectrum. But you can see similarities. Okay. Again, CH3, of course, is here. This is another CH3 stretching. Okay. There's also there's no CH2, see? So the CH2 is actually missing in between here. There's only the CH3 because the molecule doesn't have CH2. Okay. And then you have the CH3 antisymmetric bend. Okay. And then this is a double one. Okay, you see that the 1380 and 1365, there's actually a split here. And for those that are very familiar with IR, this is very typical. Whenever you have a branching in a molecule, this peak is actually split just the way it's here, because of these particular modes that show up. So this is indicative of a branching or an isopropyl type function, a split over here. So if you're very familiar with IR spectroscopy, there are a lot of details like that. You look at the band like this, you know immediately that there's a splitting, a branching in the hydrocarbon chain that occurs. Okay. And then again you have the fingerprint region. Now you can see it's still pretty small and pretty wimpy, but there's a difference here between the two fingerprints, and again this is again very typical for this molecule. Okay. So this is a branched hydrocarbon. You can see again what's indicative of the methyl group. And there's some things for the methine, but it's not shown here. Essentially, some of these peaks come from the CH function, but overall this is summarized in the fingerprint region. Okay. So this is now hexene. So we've now introduced another functional group, and that's a double bond. And you can see now immediately how much more kind of structure comes out in the fingerprint region. So this is all due to the olefin part of the system here. So we have, again, some of the methyl group systems over here. We have some over here. This is the CH3 bending, symmetrical bending. And then we also have peaks here, and we have the fingerprint. So let's have a look at this. First of all, very important is this peak. It's a small peak, but it's very indicative at this part of the side of the spectrum here. So this is an sp2 carbon hydrogen, in this case stretching, in the stretching region. So whenever you have a peak above 3000, you have an unsaturation, such as a double bond or an aromatic ring in your molecule. Okay, so any peak above 3,000, between 3,000 and 3,500, if you have these peaks, even if they're small, they immediately tell you have an unsaturation. And that is, in this particular case, at 1380, it's the antisymmetric stretch of the terminal vinyl group over here. So keep that in mind. Now, this part of the molecule is what we see. I saw before, it's methyl. There's methyl group components here. There we go. We have the methylene is now here again. Let's see if it allows me to pick the methyl. You can expand again. Okay, so that's our methyl. The antisymmetric stretch. Again, this is our olefin that shows up above 3,000. Here's the methyl. This is the methylene. And here we have the methylene and the methyl again, the symmetrical one. So symmetrical methylene, symmetrical methyl, antisymmetrical CH2, symmetrical CH3, and here we have this antisymmetrical sp2 carbon hydrogen, and then here this little shoulder, that's our symmetrical one, is there as well. You can see that the antisymmetrical is always a little bit to the left at higher rate numbers in this particular area. So very nice assignments, of course, that you can now easily pick up. This is also important. It's tiny, but it also indicates unsaturation. So if you have a peak here, you should have a little tiny peak over here. Okay, that's this nice out-of-plane bending. Okay. That's this mode that shows up here. And then we have the CC stretching. So now we have, for the first time, we have a carbon-carbon double bond stretching that's now indicative of, again, the presence of the unsaturation, and it's at 1640. So this is a carbon-carbon double bond stretching that shows up here. So this peak, and this peak, again, all indicative of unsaturation. Now, can you see these peaks over here? If we have the scissoring again, the CH2, here we would have the methyl. I can get that. Let me see if I can expand it and hit it a little bit better. Okay, so here we have the antisymmetrical bend of the CH3. Here we have the scissoring mode, that's this one. And then here we have the umbrella bend again at 1380, and again it's not split because we have a linear chain, otherwise it would be split. Then this would be the fingerprint region that comes up here. Now in this case for hexene. Okay. So a couple more. There's a big peaks here at 993. That's the out of plane terminal vinyl function. Shows up here, very distinct peak now. And there's another one which is also connected to the vinyl group. We didn't see that before. That's the terminal out of plane bend of this function over here. Again, bendings are here in the lower rate numbers. We also have two additional peaks here. They also are connected with the unsaturation, but here they're summarized also in the red highlighted zone as the, again, typical fingerprint group modes. Okay, any questions regarding this overview of the aliphatic, the branched aliphatic systems, and the alkenes so far? I'll show you a few more examples. If you have your chapter 11 handout ready, you can actually start to look at what parts of the molecules in the table, what the functional groups are that you've already seen so far. You can see, of course, in our table on the chapter highlight 11, they're highlighted with little bars over the same range of roughly 400 to 4,000 weight numbers. Okay, that's the summary. Methyl groups, methylene groups, and it didn't show the binding functions. Yeah, there we go. These are the binding functions. Okay. So in this molecule now, we have the methyl, the methylene, and then the vinyl. Again, this antisymmetric stretch, symmetrical stretch. We have the CC stretches here, symmetrical and anti-symmetrical. And then here we have the bending, bending modes where you can see the methylene group and this hydrogen across the double bond here. These are the two bending modes. Those are the new functional groups in hexene. Okay, let's do a couple more. So the alkynes are chapter 13, so we'll cover those next week. Triple bonds, you can see again my very strong peak here. We haven't seen such a strong peak before. And you can see that this now is moved. It used to be, this is the sp2 was here. This is the sp hydrogen stretch. And it's moved to about 3,300. So this is an indication, very typical of this stretch, right? sp carbon hydrogen bond stretch. We already know what these are, so I'm not going to tip on them again, but there's another one that comes up. So let's see what this is. This is our triple bond. Remember the double bond? We had a tiny peak around here before. The triple bond goes to higher rate numbers, right? It's higher in energy. It takes more energy to stretch a triple bond. That's why it's moved to the left over here. Okay. Again, we know what these are, right? We have the scissoring bend here. We have the methyl antisymmetric bend. We have the CH2 here, slightly shifted. The CH3, the umbrella. We have this little mode. That's not a very typical kind of a mode on the methine here, on the sp3, sp hybridized carbon. Shows up here, so this is very difficult to see, often can be missed. It's like almost part of the fingerprint, but you can see already this is the this is essentially the overtone of this stretch. So this goes in combination with a much bigger peak, which is this peak. Okay. And you can see what the overtone means, right? If you had physics, classical physics, particle in the box, you can have 2n, 2 times the frequency. So this is 2 times the frequency. This is slower, and this would be twice as fast. That's the idea of the overtone. It's the first overtone of this particular frequency. So this is this bending mode, big peak here, and then some kind of a small, relatively broad peak. That's the overtone, is 2 times the frequency. And then, of course, again, you have the fingerprint region typical for a molecule. Okay. So these are now the new functions in the triple bonds. So if we add a triple bond, again here we have 3,300. We have this stretch over here. Then we have a stretch here, the CC stretch over here. And then we have bending modes, including this bending, which is very typical here. We don't usually see such a big peak in a hydrocarbon unless there's an acetylene and alkyne here with a CH attached. Okay, let's look at a nitrile. Just really quick, what are the typical features here? The nitrile. In this nitrile, obviously we have a triple bond, but it's not a carbon hydrogen, it's just a nitrogen. So all we see is this stretch, and you can already guess what this is. This must be the triple bond nitrogen stretch. And that's exactly what it is. And of course, missing is the part of the triple bond that has a hydrogen attached to it. These are all missing because there is no hydrogen on the sp carbon, right? So these are gone. And then the rest of the molecule looks very similar to what that hexane would look like, right? That's the part that carries that that functional group. All of this we've seen before. Okay, that's an interesting molecule. So let's look at some aromatic molecules. Now in the aromatic molecules, we have a bunch of sp2 hybridized carbons, and here in toluene, we also have a methyl group. So it will be a combination of a hydrocarbon without CH2 groups, those are missing, and then an aromatic function. And so immediately what you see is above 3,000, we have these peaks. Very indicative I also mentioned we have these peaks now. Now, since we have more than one type of double bond here, we actually see 3 of these little peaks here. They all kind of come together. These are the CC double bond stretchings. So this one, these peaks here, not surprising. Those are the aromatic functions, above 3,000. You see the aromatic ring here? So aromatic CH stretches. And these would be the CC. This is a combination of overtone, again, they're the double bonds in the toluene molecule. So these CC double bonds here. Okay, this peak over here is a very interesting one, but it's in practice difficult to see. It's almost sometimes part of a broader background here. There's kind of a big breathing bubble. And then maybe most typical here are these peaks again down here. And those are the out of plane, symmetrical out of plane, and kind of an unsymmetrical out of plane. So 2 peaks here and here, and then there's another one down here. Okay. All that's part of the fingerprint here, but it often covers the aromatic systems. Okay. And so what's interesting about these 2 peaks is that if you have enough data for analysis, they actually give you the substitution pattern. So based upon these peaks, you can tell where the substitutions are, because obviously, this includes all the atoms that are connected to the aromatic ring. So if you replace one of these hydrogens with an alkyl group or a methyl group, then these peaks will change. So this is a very typical range where you can read out from the position of these peaks and the type of these peaks, you can read out if it's an ortho, a meta, or a para-substituted aromatic system. So again, very indicative for diagnostic purposes. Okay, so these are the peaks of the aromatic systems, both the CC double bond and the CH systems. It's kind of a summary here. Again, very indicative for us is this and this. Maybe this is not so indicative, but this again indicates actually the substitution pattern is these outer plane ring bends and hydrogen bends. Okay, alcohols. Again, hexane plus an OH. Where is the OH? Well, obviously it's here. Right? That's part of the OH, because if you remember the rest, maybe here too. So if you just look at the hexane, or remember the hexane spectrum, and then the hexanol spectrum, well, this peak clearly must come from the OH, and maybe this peak as well. The rest, of course, remains the same. And of course, the fingerprint always changes. And so the OH leads to a bunch of really broad peaks. This is the most obvious one. That's the stretching, the OH stretching. Okay. So how can you differentiate between an alkyne and an OH stretch? How would you do that? So why do you know that this is an OH stretch and not an SP hybridized carbon hydrogen stretch? Yeah?
It's very broad.
Yeah. So the line width. Okay. So when you look at an IR spectrum, what you're looking at is the frequency or the wave numbers. You look at the intensity, because they're different intensities, and you look at the line shape. And you use all 3 pieces of information to make an assignment for a particular functional group. So that's when you're a specialist in this area, that's what you consider. You look at all of these aspects. You look at the frequency, the line shape, and the intensity in order to come to a convincing assignment. And you generally use more than one band to confirm the presence of a functional group. So the alcohol, okay, you also use this particular bit peak here, because this involves the stretching of the CO and the CC bond. So it's a CO stretch, but in this case it's coupled with the CC stretch of the neighboring carbon-carbon bond. So this gives you the kind of ether component, has to be there, and then this is the OH component in our alcohol. Okay, so I didn't mention this. This is difficult to see. Also, this is often difficult to see. But the typical ones are this one here, and then this one here for our alcohol. Okay, let's see what else we have. Maybe one more. The amine. Amines are a little bit difficult to see, but amines have an NH, but you can already tell this is in the same range as our OH, but the intensity is a lot smaller. So it's a broad peak. Same frequency as the OH, but lower intensity. So again, remember, you look at three aspects: intensity, frequency, and the line width, or the shape. And so this is something here that has very much similarities to the hydroxyl function, but it's much lower intensity. Also, it's split. Why is it split? Anybody knows? Why do you see two peaks here? Very simple. Because there are two NHs. Okay, so by the number of peaks here, you can actually read out how much hydrogens are on the nitrogen. Because if there's two, then there's two hydrogens on the nitrogen. So it's a primary amine. Okay? This is one. You see the lone pair here. This shows the lone pair. And then you see the other. Okay? Symmetrical and anti-symmetrical. Of course, you can only have those two if you have two hydrogens. Right? If there's one of them is a carbon, then it looks different. You'll only have one peak. So you have only one stretching, so they kind of combine. So symmetrical and anti-symmetrical collapse if there's only one image. Okay, and then you have this peak again. This is difficult to see, but it is this bending mode, the scissor bending, and then again this one is another bending mode. It's the so-called lagging mode, lagging around, but often sometimes difficult to see as well because of low intensity and because they're at the liberal. But this one is very typical for a primary amine. Okay, let's do a couple more. Aldehydes, ketone, carboxylic acid, and then we'll stop. So this is the aldehyde, and I definitely need to point out the CO. Okay? The carbon-oxygen double bond. Very, very important. So this is the most important new peak that we want to see here. That's the CO stretch. Carbon-oxygen stretch at 1720, 1727. So that's a very important peak. The carbonyl stretch, you can see it here. It's very strong. It's often the most intense peak in the spectrum. It's relatively sharp, not too sharp, but relatively sharp. And it's a very typical range. And so this is a great indication for a compound that contains a carbonyl group. So very important, very typical. So 1720, one of the most important peaks in the NR. There's some other peaks, as you can see, but this is really the important peak. Sometimes you see this, again, this is sometimes difficult to differentiate from the methylene stretches, but this is the important peak for our carbonyl group. The ketone, a little bit different, right? But also has a carbonyl group, and indeed, again, 1720, most important peak here, new peak, is our carbonyl group, similar to the aldehyde. That's our carbonyl group. That's the overtone, sorry. This is the overtone up here. Usually you don't see that. That looks like a little speck. That has twice the frequency of this peak, 1715. Okay, so the overtone is the little one over here. This is the one that's the same. I pointed out. For those of you who look very carefully into the last aldehyde spectrum, there also is an overtone here. These are all, some of the really big peak, intense peak always have an overtone coming at twice the frequency and twice the wave numbers. Okay, and then let's do the carboxylic acid. The rest, you know, remember that, I think. Okay, carboxylic acid. So carboxylic acid is a carbonyl group and an alcohol together, right? And so you see the alcohol part, really ugly here, and then you see the carbonyl group, again, very typical like the ketone here. So that's important, and that gives you the combination. So an OH, an OH, this case, it has a dimer. So they dimerize in solution here. This is usually in a sample where they can dimerize, so they combine one carboxylic acid, takes hydrogen bonds, another carboxylic acid, and then, of course, this ketone function here. The ketone function. That's again at 1711. So everything, all the carbonyl groups that we're dealing with, generally between 1700 and 1730 wave numbers. Okay, that's it for IR spectroscopy. Are there any questions? And so, if you're really good in spectroscopy, you can actually use it to assign structures, particularly if you have a database. And if you're not so good, you can read out a few functional groups. So IR is great to read out a few functional groups. That give you an idea if there's a carbonyl group or not. You can things like that you see immediately. If there's an amine, if there's a triple bond, a double bond, an aromatic, all these things are pretty typically very quick information that you can gain from that. And it is a useful tool, mainly because it is so portable, so straightforward, and you can analyze all kinds of samples. Even their mixtures, you can still get some ideas about what's in it. Okay, let's do a little bit more on mass spec and go back to our slides. Okay, and so in the book, you can look at this again now, look at the tables and the data in the book on IR. This is from the book. You can see these assignments now color-coded. But this the motion in the program that I gave you, I think you can get a better appreciation of what's actually going on physically in these vibrational modes that are color-coded here. You can see the IH, the CO that I pointed out before. And you can see in some of these compounds now that the fingerprint region, of course, is much stronger. So really very big differences in the fingerprint region, and you kind of have to read out the functional groups in this system. Okay, so again, this table shows you some of the typical assignments for wave number ranges that I also pointed out. This is just another way, an overview that I made that shows you a little bit more different resolution, different type of table, what the typical areas are for certain types of functional groups. Okay, but also let's look at mass spectrometry. And so I have here from the book just a spectrum that's a typical MS, and you can see this now looks very different. It doesn't look like bands or anything like that. So this is spectrometry. This is highly digitized. So spectroscopy, you kind of look at the absorption or transmission of light. It's a very direct measurement. In mass spectrometry, you have a lot of electronic reworking of the data and display of the data. So it is not as direct as a spectroscopic tool. So that's one of the reasons why we differentiate the nomenclature a bit. So this is not really something that you can read out immediately. This is some kind of a detector. This is a digitized and electronically display, or different in a graphic way, a very different display from what you've seen before. So this doesn't mean there's an absorption here or some kind of a differential transmission. This means that we have species that have this molecular weight that are counted and then kind of calibrated to a relative absorbance. So the type of detector is very different, and so the readout is not directly correlated, not be correlated to any interaction of light as you have in a spectroscopic technique or radiation in the spectroscopy technique. So, but you can see immediately what I pointed out before is through the mass spec, ultimately you get the formula. And starting point for the formula, the chemical formula is the molecular weight. So one of the direct readouts that you get in mass spectrometry is obviously readout of the molecular weight. Okay. So in this case, it is N plus dot. So what you do is you ionize a molecule, essentially generate a positively charged radical by kicking out an electron from the system by a bombardment of some sort. And then you accelerate those, and then you measure how fast they transfer through a certain distance or how much they're bent by a magnetic field. And then you use that via calibration, via an internal standard that you get. You then use that to display a number for a particular ion that then hits a target and leads to a little a current that's being formed. So again, it's not a direct technique. It requires calibration, big setup, and also computational analysis of the data output before it's displayed in this version. So each one of these bars means relative abundance versus the maximum peak of other peaks. It's calibrated internally, and then these are different molecular masses. And you can only get these masses in a relative sense and by using a standard. And so this is m over c, it's mass over charge. And charge usually is 1, and if it's 1, then these numbers correspond to the mass of the molecular ion that you generate. Indirect technique, nothing to do with the transmission of light in these systems. You can also see, besides the molecular ion, you see these fragment ions that are indicated here. So this is just simple pentane. Molecular mass is 72. This is the molecular ion, mass 72. You can lose a methyl group, get a really tiny relative abundance. The biggest abundance is a minus an ethyl group. So we also fragment the molecule. We break it into pieces. Obviously, when you knock out an electron in the molecule, you accelerate it, it's charged, it starts to fall apart. And that's shown here by the presence of these different ions that you can see here that are assigned here to these masses. So you also get some information about smaller parts of the molecule when they start falling apart. And so this is the mass spectrum of butanol. And in butanol, you can see now the molecular ion is really tiny. That's part of the problem. It depends on the ionization method. There's lots of different ionization methods. You could give an entire course easily, for an entire semester, just on mass spectrometry with different ionization techniques. In this so-called electron impact ionization, we often have the molecular ion being relatively small. And so you just assume that the ion is the highest molecular weight is the molecular ion, but in some cases that might not be the case because it just falls apart before we can detect it. And then you have to use different ionization techniques. This is a minus a hydrogen, also positive charge, minus water, you get elimination. The water molecule is indicated here. This also occurs in the mass spectrometer, and you get this particular ion here. And then again, you see just in this case, the CH2OH plus, that's a fragment again coming from your molecule. And so are these peaks over here. So that's how these mass spectra look. And this is a little bit of the theory here behind it. So let's look at benzamide, and we are using here a technique I already mentioned, EI, electron impact. You bombard the molecule with accelerated fast electrons. They knock out, like in billiard, they knock out electrons from your system. High energy beam generates these positive ions. So plus an electron, you knock out another electron, they disperse. You end up with a positively charged benzamide radical, which has still the molecular weight. It has the molecular formula is still the same. We just changed it. We took out an electron. That doesn't change the molecular mass. And so you get the molecular ion which you can detect. And so the measurement of mass, of course, ultimately you can do this at very high resolution rather than just having full numbers. If you have sufficiently sensitive mass detectors, you can go into these subparts, very small parts per million or per thousands here of the actual number. And so that allows you now to differentiate between different molecules. So here you can differentiate between an NO and the CH2. They both have the mass of 30, but they differentiate because they have different elemental composition. The digits after the period are different. That's true for all of these species. So these